Okay, hello everyone, and welcome for this workshop session. Today, the idea of this workshop is to present you and to introduce you a new platform for complex emulsion generation. And so the idea of this workshop is to have together, as we are a small group, the idea is to have nice interaction and good discussion together. It's not a huge webinar with a lot of attendees, so I'm encouraging you to ask a question. Feel really free to ask any type of question related to what we are going to present, but also if you have any type of question regarding microfluidic emulsion in general, feel free to ask as well. And also if you have specific question to your application. So to this purpose, you have two options. The first one is to use the Q&A panel available at the bottom of the Zoom session. So you have the Q&A button. So we will see your question. We will repeat the question for everyone and answer it. But also you will have the ability and the possibility to ask directly question by turning on your microphone if you want to discuss directly with us. So it is also possible, and this is something that we are going to allow on this workshop to have, again, good interaction. So to this workshop, let me briefly introduce you the team who will be presenting today. So from my side, so my name is Adam Mezian. I'm working at Fluigent as project manager. And my work is focused on droplets and particle production for different kind of application. And on the other side, we have Youn Vitry and Adrien de Waal, Sequoia Technologies. And Youn and Adrien, they have strong expertise in droplets, droplet formation for any type of application, and also encapsulation of active ingredient inside microcapsules, and for any type of application. So it's time to start. I think we have everyone on board. So Adrien and Youn, I'm giving you the lead.
Okay, thank you, Adam. So hello, everyone. I'm Youn, and I will start with the Redrop device. So maybe some of you already know this device, maybe some don't, and I will start by the beginning, I would say. So the Redrop device is a microfluidic device based on the capillary technology, I would say, on which we use 3D printed nozzle to have really repeatability from one device to another device. It is composed of a main chamber that you can see here, on which you have on the left part the injection insert. In this case, this double nozzle, and on the right part you have a collecting insert to collect the emulsion that we produce. As I said, so in this case, and so in the case that of the pictures that you can see, it's a device to produce double emulsion. But if you want to produce simple emulsion, you simply have to change not the collecting insert, but the injection insert to simple emulsion injecting insert. And if you want to, each insert will give you some range of emulsion that is achievable based on the flow rate applied. And if you want to switch from one range of size to another range of size of emulsion, simple or double emulsion, you can change the insert and change the dimension of the extraction capillary and the nozzle, and you have a different range of emulsion. On the picture in the middle, you can see a zoom in of the Redrop, where you can see the injection nozzle on the left part. So in this case, it's a double emulsion nozzle, and the right part you have the extraction capillary where we collect the emulsion. And in the picture just below, you have the simple emulsion nozzle to produce simple emulsion. So it's really just one entrance, and the other one has two inlets for the core and the shell phase. And on the right part, you see the formation of double emulsion. So as it is axisymmetric geometry, so the core and shell phase never touch the wall of the extraction capillary. The condition phase will surround the rest of the liquid, the nozzle and the extraction capillary. And when you inject the core and the shell phase through the nozzle, it will create in one step the double emulsion. And this design is easy to disassemble and to clean. That's really one of the main focus of this device, to be easy to clean because of clogging from dust or polymerization of the polymers that you are using. And you can really use it in different configuration. What you can achieve with this device is the production of double emulsion for water in oil in water double emulsion, as you can see in the picture on the left of the top left, where you have water in dissolved in water and water in mineral oil in water emulsion. But you can also do with the same device oil in water in oil double emulsion, because there is no surface coating that is needed to produce the emulsion. Because once again, the geometry is axisymmetric and the core and shell phase never touch the wall of the system. So you never have wetting issue. And one also great thing that you can do is partially miscible double emulsion. As you can see at the bottom of the slide, in this case, it is water in ethyl acetate in water. Once you have set your emulsion process, you can adjust the shell thickness of your double emulsion by simply playing with the flow rate of the core and shell phase. And on the performance range, you can reach a high frequency of generation, more than a kilohertz. In the standard configuration, you can produce double emulsion between 80 and 150 micrometer. But if you want to go below or higher from this range, you simply have to change the injection and the collecting insert to achieve a larger double emulsion or smaller double emulsion. And the monodispersity is really great because you have a PSD below 2%. And what we can do with it, I will let Adrien present you some use case.
Thank you, Yoon. Now that you know how the Redrop works to produce simple and double emulsion, I will just give you some insight of what you can do with it. It will be, of course, a non-exhaustive list, and I will focus on double emulsion and the production of microcapsules. By microcapsule, I mean a solid shell and a liquid core, and this microcapsule is obtained by the cross-linking of the shell phase containing a polymer in the tubing connected to the output of the Redrop or in the collection reservoir. And depending on the polymer that you use, the cross-linking can be induced by different systems: UV light, solvent extraction and precipitation, or a chemical trigger. The result, the output of the system is monodispersed capsule with a solid shell that you can see on the slide and a liquid core, and in which it is possible to encapsulate API, biomaterial in solution or in suspension. As a first example, we use UV light sensitive resin as a shell, and we cross-link the shell in the output tubing with a UV LED lamp placed above the tubing. The result in this case is a liquid water core surrounded by a solid resin shell, and it is possible to encapsulate some molecule in the aqueous shell in this case. In the next example, we produce hydrogel microcapsule with a ketosane shell, 2% in water, and oily core. In this case, the core is soybean oil with a red dye to increase the contrast between the phase, and the continuous phase transporting the droplet in the output capillary is octanol with span 80 surfactant. In this case, we produce double emulsion, and we cross-link the double emulsion in the collection bath, so ex situ polymerization. And due to the fact that we use the good surfactant in the shell phase and in the continuous phase, we have stability, and the droplets are stable, no coalescence during the time of cross-linking. You see the result, the shell thickness after 4 minutes on the image on the bottom on the left, and then after 1 hour in the cross-linking bath. In this case, it's possible to encapsulate lipophile compounds in the core, in the oil core. It's possible to encapsulate volatile products. And we demonstrate that there is a very limited leakage. So the dye release was less than 5% after 24 hours. And at the end, it's possible to release the content of the droplets of the capsule using an acid trigger. In the next example, we produce a microcapsule with a PLGA shell and a water core. The cross-linking of the PLGA results from the solvent extraction and precipitation from the shell to the continuous phase in the output tubing and in the collection bath. So the cross-linking begins in the output tubing and then continues in the collection bath. And you see the same as with the ketosane, you see the results 15 seconds after the collect and then 200 seconds after the collect in the water bath, PBS in this case. Using this setup, you can, by example, encapsulate water-soluble API or biomaterial, and then you can release this material in the gastric system when the PLGA will be dissolved. So PLGA is well used in the pharma world because it is biocompatible and FDA approved. Then you can play with the solvent because the PLGA is dissolved in a solvent. You can use, by example, ethyl acetate or IPAC or dichloromethane. And by playing with, by changing the solvent, you can adapt the porosity of the shell and the size of the shell. And you can also play with the content of PLGA in the shell. In this case, that is 2% of PLGA. Okay, now so let's go to the presentation of the platform with Yoon.
Yes. So a standard microfluidic setup is something that you can see on the screen. You will have some pressure controller to pressurize the continuous phase, the shell phase, and the core phase. You will place some inline filter to avoid any clogging. You will have also some flow meter to measure the flow rate of your system. Then you will have the Redrop here, and to start and stop the system, you will use some valves because it's really difficult without valves to start the system. And then once you have produced your emulsion with the Redrop, you can either directly collect it to observe them or to do ex situ processing, or you can also connect the Redrop to a microfluidic chip like chip chop or micronite or any PDMS chip of your kind to further analyze your system. But as some of you may know, when you do microfluidic experiment, you have a spaghetti of tubing that is really difficult to handle on a lab bench. So what we did is to implement all these setups that can be quite complicated sometimes into a small platform that you can see in the picture. And I will now switch to a live presentation to show you what we did. And I will stop sharing the screen so it will be more smooth. So you have the platform here. So it's really here to help you have a clean lab bench and not something like you have tubing everywhere, a huge microscope on the side. Everything is included actually. So you will have some pressure controller at the bottom that will pressurize the reservoir for the continuous phase, the shell phase, and the core phase. What we did for the shell phase and the core phase is use 2 reservoirs for each. And you can switch between one reservoir to another with the valves here on the top of the system. This is really here to help you have an easy way to produce your emulsion, because when you do polymerization system, for instance, or you use an API into the core phase that you want to encapsulate, you will prime the system with pure solvent or close to pure solvent. And when your system is ready and stable, you can switch to the polymer reservoir, the solvent with the polymer, easily. And when you finish your experiment and want to clean the system, you can switch back to the pure solvent to clean the system and avoid any clogging or polymerization inside the tubing or inside the Redrop. Then you have filter in the back to really prevent any clogging. So you have a 10 micrometer filter for the continuous phase and 2 micrometer filter for the shell and core phase. You will then have some flow meter to measure the flow rate. You don't see them on the screen, but they are here right behind. Then you will have here on the valves panel. And these 3 valves are here to easily start and stop the system, stop the flow rate, restart an experiment when you have some trouble. The valve will allow to direct the flow from the reservoir here to the waste on the side or to the Redrop that is here. And it will be the same system of valves for continuous shells and core phase. Now you have here the Redrop and the optical system. So before going to detail into this, I will just show you the red drops that you can see. So you can see the size of a double emulsion red drop. And here you have the, on this side better, you have a simple emulsion red drop. So you can see the size of the device, and you can see that you have the insert on both sides that you can dismantle if you want to clean it easily, and thanks to the two screws here. And so on the optical system here, so you have a powerful LED system, microscopic objective, and a small USB 3 camera that is a colored camera. And so it's really perfect for the observation of the emulsion, and it will be sufficient for most people. You can replace this camera by high-speed camera if you want, but of course it will cost a lot. And to complete the system, you will have on this side two micrometric stage to adjust the focus of the system in the observation area. And on this side, we'll have a long X stage in order to analyze what is happening inside the red drop, or to analyze what is happening after in the tube. It can be really helpful when you have some trouble in a polymerization process, for instance. And now to start the system, I will switch to this screen. Yes. So to start the system, so the red drop is already filled, the main chamber is already filled with the continuous phase to gain some time. In this demo, I will put some pressure on the continuous phase, so you can see the flow rate. When it's stabilized at around 200 microliter, it's really perfect. So at the top of the screen, you have the pressure controller system. So the continuous phase here with the pressure controller part and the measurement of the flow rate. Then you have the shell phase here with the pressure and the flow meter, and then the core phase here. Now that you have a stable flow for the continuous phase, we'll start by doing the emulsion of the shell phase. So once again, I set some pressure. I will switch the valve from the reservoir to waste, and now from the reservoir to the red drop. So you have directly an emulsion that is forming. Sometimes you might need to increase the flow rate in the shell phase to clean the nozzle, and to be sure to have something that is really neat inside and oil everywhere in the shell. Once you have droplets that is forming and are clearly forming, you can decrease the flow rate, the pressure, and so the flow rate on the shell phase. And we can now switch to the core phase. So once again, we set some pressure on the core phase, and with the valve. So the valve for now is set from the reservoir here to the waste on the left part. It was the same for the shell previously, and now I will switch the valve here from the reservoir to the red drop. So in this case, it works instantaneously because we use experiments this morning, but sometimes it can take a bit of time, a few minutes just for the flow to arrive to the nozzle. You just have to wait a few minutes and it will be working, as you can see. Of course, what you see on the screen is just a few of the double emulsions that are formed, because the camera here is set at 15 frames per second to be sure that you are able to see the droplets and the emulsion, but the real generation frequency is much higher. And once you have set up your emulsion, what you can do is play with the flow rate to either adjust the shell thickness or the size of the emulsion. For instance, if I decrease the flow rate on the core phase, like I'm doing now, maybe not too much, but you can see that the shell thickness is increasing. And you can do also the same if you change. For instance, now if you want to increase the size of the double emulsion, what you will do is decrease the flow rate of the continuous phase. So by decreasing the flow rate of the continuous phase, you will see the double emulsion that is increasing in size. And if you want to decrease the size of the double emulsion, you have to increase the continuous flow rate. And once you have generated all your double emission, what you can do is collect them if you want to observe them. Yes. And so that's the double emissions that we just produced. I think I forgot to say a word about the phases that I'm using here. So in the continuous phase, it's water with twin 20 as a surfactant. For the shell phase, we have mineral oil light with abyl 90. And for the core phase, we have water with twin 20 and some blue colorant to have a better view of the double emission. And if you have now any question, we'll be really happy to answer them. So feel free to ask any question.